today's video, we're going to be discussing the ideas of mass energy, equivalence, and resonance. So, to have a preliminary understanding of resonance, which is probably the more intuitive ideas, surprisingly, the more intuitive idea out of all these ideas, because for mass energy, E equals mc squared is very mainstream and is like very well discussed. Is already discussed, but not very well understood necessarily. But it's not necessarily a pretty wild idea. Necessarily, it's like pretty common in public awareness, public general awareness. But it's not very well understood at all. And also, mass is like everyday. It's an everyday colloquial conversations, not even necessarily scientific conversations, but there are ideas that are not very well understood. But in order to understand those ideas very deeply, we should probably start with resonance. Resonance has to do with so basically anything with mass, and there is a law for this particular equation, and the quantity I'm referring to is the resonance frequency. So the phenomenon of resonance has to do where you have maximal coupling, you have efficient coupling between an oscillator, maybe a harmonic oscillator, and some wave system. So wave is just a conventional way. It's probably the default standard way of exchanging energy in the universe. Energy in the universe, in the physical universe, is usually exchanged via a wave, and the maximum efficient energy coupling uh, happens when you have energy exchanges uh, in terms in integer multiples of the resonant frequency. So for any mass in the universe, there is a corresponding resonant frequency. This is classical mechanics, so we're mostly speaking about mechanical waves, or any viable physical analogy to mechanical waves, where energy is transmitted and energy more or less obeys classical mechanics. And so every mass has a resonant frequency, and essentially mass could be measured by frequency. Every mass has a frequency. Roger Penrose famously said that essentially a mass is a clock. That's the most physically fundamental way of measuring time, is just measuring the natural frequency of a massive object. Any massive object has a natural frequency that has to do with the resonance frequency. This is understandable from the point of view of classical mechanics. And there's an energy equation, like the most basic fundamental equation for resonance frequency is equal to the square root of Hooke's constant divided by m. Whatever k is in classical mechanics, I think it's Hooke's constant. Anyway, so resonance really gives you a really proper idea about mass. And if you're to look at like the quantum scale, you can also think of resonance at a quantum level. So for atoms have different atomic weights, and the idea of mass here is again relevant if you want to talk about resonant frequency. Atoms, interatomic energy exchanges only occur in integer multiples of particular frequencies, and these energy exchanges are mediated by the photon, which is a wave, which is an electromagnetic wave, is a quantum wave as opposed to a classical wave, so it behaves as a particle as well. But essentially it's the same thing, because these atoms have intrinsic energy levels which are correlated with the mass of the atom, which is indirectly measured by the atomic weight, which is how many protons and how many neutrons it has, which is going to dictate how many electrons it can accept. But this natural order, this natural architecture is also quantized, and the minimum energy that an atom can accept during absorption, during electromagnetic absorption, is going to be this particular atom's resonant frequency. So it can be understood as such at the quantum level as well, which is, I would say, the most intuitive way of approaching quantum mechanics. But I would say it's the most intuitive way of uh, understanding what mass is in relation to energy. For exchanges between matter and massive particles, they may very well be also molecules. For molecules, to a certain extent, also behave quantum mechanically, I should say, rather say, and they're going to exchange, they're going to have intermolecular or interatomic energy exchanges that are quantized uh, at the specific resonance frequency. So that, I would say, that is the connection between resonance and mass, which is which I guess is I would say is more intuitive than other a great many other approaches to quantum mechanics. Um, Now, for the second part of the video, we'll be discussing inertia and mass. For the third part of the video, we'll be discussing mass energy equivalence. And for the last part of the video, we'll be discussing resonance as it relates to like every concept that was discussed in the video, such as to be able to wrap up the video very efficiently. So basically, what is inertia and mass? What is there a distinction between inertia and mass? That is a very good question. So let's really dive into how these ideas really appear in physics and how are they understood according to the theory of modern physics, or classical physics, or just physics generally. So basically, mass is mass is inertia. Essentially, this is, well, let's just tackle the question, directly. Mass is inertia. So mass is inertia, and there's actually two ways to think about inertia. Inertia is the more general idea. Mass is pretty like specific to like atomic physics and like molecular chemistry and so forth. But inertia is a very general idea. It could happen at the macroscopic level in classical mechanics. It will be relevant at the quantum level. It will be relevant in any theory. Inertia is a very general idea, and actually not only characterizes mass but also state of motion. Inertia more or less is implicitly contains the idea of a state of motion and also the idea of mass. So inertia is a more general principle. You might also think that you might as well think that inertia is the more fundamental idea as opposed to motion or mass independently. Anyway, so so inertia is basically in the mass understanding of inertia. Mass is really how difficult inertia is really how difficult it is to stop or change an object's state of motion. So basically, if something is moving, how much force would you have to apply in order to stop it, the state of motion of that particular massive object? Or if the object is you're in a system of in a coordinate system where you're at rest with respect to that object, how much force would it take to accelerate that object and set it into motion? So that would be inertia. How much inertia does that body have? For essentially, if it's more massive, intuitively everybody can understand that in order to set it into motion or to stop it, if a truck is coming at me, if it's very massive, it's more difficult to stop it. And this is really the result of well, it's not the result. This is in nature, but this is encoded in Newton's second law of motion, which is F equals ma. Either the first or the second law of motion. I think it's the second law of motion. F is equal to ma. F is equals to ma tells you that mass is obtained by force divided by acceleration. F equals ma also tells you that mass is a multiplier, is a direct factor of the force. Is the independent variable that is going to determine the force. For if mass has a larger magnitude and the acceleration is constant, you would like to produce the same state of motion, a particular acceleration magnitude. For acceleration is a vectorial quantity that also has magnitude. You would like to produce the exact same state of motion for objects that have different masses. For the larger the mass of the object, proportionally, that is going to require a lot of force in order to be able to do so. So that is encoded in F equals ma. That's essentially what inertia is. Inertia is how massive something is, which you're really trying to say is how difficult it is to move an object. That is essentially what mass is also, right? So if I speak of the inertia of a body, and I speak of the mass of a body, phenomenologically, or from the point of view of observation, or from the point of view of tangible measurements, I would use the same method in order to determine the inertia or the mass of the body. You might as well say they're the same thing. In physics, they're essentially the same thing. But also, okay, so there's also a motion part of inertia, or linguistically, as it is used in physics. You might also understand inertia as a natural motion of an object, where the sum of the forces applied on that object are equal to 0. What do I mean by this? So basically, this is actually Newton's first law. This is the law of inertia. F equals ma is more so a law of motion, but explicitly within the initial enunciation of the laws of Newton, he explicitly describes the phenomenon of inertial motion. Inertial motion is the natural motion of an object, albeit a massive object, but I would say we should have the reflex as physicists to have a general approach to ideas. You should probably try to figure out what is the more general idea in order to make room for future predictions. We should not be so quick to say that inertia is only something that occurs to massive objects. But anyway, like implicit in the Newtonian formalism, we're talking about a massive object. The principle of inertia says that if an object is moving at a particular, has a particular state of motion and no forces are applied on it, it's moving inertially. That is to say, it's moving at a constant velocity, which could be in certain coordinate systems be 0. Inertia is the natural state of motion of an object. If there's no force applied on an object, it will move inertially. For instance, if I have this object, which is a pen, which has a particular mass, has a particular natural inertia, and in my frame of reference, it's not moving, and I'm not applying any force on it, it would continue to remain in the state of motion, which is to say that it will not suddenly move. So it's moving inertially in my system, in my coordinate system, although if it was moving at a particular velocity and no force is applied on it, it's also going to tend to continue to do so. It's very likely that it will not suddenly stop moving unless something is acting on it. So I think that really should tell you, these things really go together, for nature is very symmetric and very harmonious. But you should really think about this very deeply, because I've just described inertia in two different ways that are not necessarily self-evident that I'm really referring to the same idea. For one, I'm referring to a state of motion where the sum of the forces is equal to 0. But firstly, what I was actually conveying is the idea that inertia is equivalent to mass, which just tells you that we use language very poor in physics. These are actually they should be two separate ideas. But the inertia of a body is how difficult it is to change that state of motion. And also, inertial motion is any type of motion where you're not trying to change the state of motion. So that is essentially what inertia is. there is inertial motion and there is inertia per se, which is something which is characteristic of bodies of mass, which is to say how massive the object is. But let me just expand, and this is not established physics, but let me just give you an example of how general this idea is. For instance, what is the natural trajectory of a ray of light in a gravitational field? I mean, well, the gravitational field has a space-time geometry. This is understood from general relativity. So it would follow probably a curved trajectory according, which is going to be more or less curved according to the intensity of the gravitational field. So the ray of light is moving inertially, and inertial motion really depends on the geometry of space-time. But if a ray of light has a natural state of motion in a particular space-time, well, hence this, you have to say, according to the definition of inertia, that this ray of light has inertia. It's moving inertially in a curved space-time. Well, would it be difficult to change that? Yes. Well, you would have to apply a force. How would you apply such a force? You would have to increase the intensity of the gravitational field, which is going to add more curvature, which is going to change the inertial trajectory. Well, the geometry of the trajectory, which is whatever is a natural trajectory of the ray of light. Well, I think if you're very courageous in that particular instance, or a bit crazy, you might actually say that the ray of light actually has mass, for it has inertia. Anyway, but this is not the point of the video, but I just want to say that inertia is a very general idea. I know it's usually used in terms of math, and this is how you should properly discuss it in terms of theory. And if you're solving probably a physics math problem or a physics problem or physics understanding, or writing about physics in a standard paper or at the university level. But obviously inertia is a very general principle that has to do with a state of motion where there's no forces applied on an object. What specifically in terms of the history of physics, we usually discuss a massive object in this case. Okay, now for the third part of the video, we're going to talk about the mass energy equivalence. So for the mass energy equivalence, Einstein discovered, playing with equations and using a thought experiment, what would happen if you heat up a massive object? And he had this equation of, the relativistic momentum of an object. And you can think about the object at rest, and as opposed to a relatively moving system of coordinates, and you have another situation, and you can try to think about what happens energetically to that object as it absorbs radiation in both of these cases, from the point of view of observers who have two different states of motion. It turns out he was able to find mathematically that if an object gains radiation, which is to say that the temperature of the object is increased, that it would gain mass. This is pretty easy to understand. I think we're gonna go through this very quickly, because I think it's pretty simple. So basically, this is my understanding of it, to the best of my knowledge. If you have another idea, feel free to comment on it. I think this is the most proper understanding. So basically, what is mass? Mass is essentially, classically, is defined as force divided by acceleration. Well, if you're thinking about an earthly observer, or an observer in the universe, there's also gravity. Well, I mean, essentially, Euclidean Minkowski geometry doesn't exist. Nobody has ever seen it. There's always gravity. So you have to probably define mass in terms of gravity, because that is what is going to be true for observers. Anyway, a definition of mass in classical physics, which is entirely valid, is force divided by the gravitational intensity. So mass is essentially how much force is applied on a system. Right, so if you think about an observer trying to measure a mass in a gravitational field, he would use a scale, and that scale is going to measure how much pressure or how much mass is exerted upon the scale, and the intensity of that force is a proxy for mass. All you have to do is take the magnitude of the force and divide it by the gravitational intensity, g. Right? This is resultant from the equation of the gravitational. This is the equation of weight. The equation of weight is force is equal to mg, and if you want to solve for mass by rearranging the equation, you're going to get mass is equal to force divided, or weight divided by the gravitational intensity, or the gravitational field strength. That is a factor of altitude, because if you're closer to a source of a gravitational field, the intensity is much higher. So you just have to change the settings of your scale to adjust and change whatever number you want to take for the gravitational field strength. But essentially, mass is how much force is applied on the system. So dividing force by the gravitational field strength will give you mass in the gravitational field. Okay, what does that have to do exactly with mass energy? Well, basically, if you add temperature to a massive object, it's going to vibrate more, and it's susceptible to apply slightly more pressure, or apply a slightly greater force, all things considered, on the scale for an observer in the universe where everywhere there's gravitation. So if he wants to measure mass, a very good way to do this is to just use a scale in the gravitational field, and provided that he actually has a number or a definite magnitude in the unit system that is convenient to him and self-consistent with the other quantities he's trying to measure of the gravitational field strength. If he has that number, then what he will need to do is measure the force applied on the scale and divide it by the gravitational field strength according to his data on the gravitational field strength in his immediate vicinity, essentially. And well, if mass is the force applied on the scale gravitationally by the equation we've just discussed, well, that force is going to be slightly increased if the object absorbs radiation. If the object absorbs radiation, it will vibrate more, which is going to apply slightly more force on the scale. So that would be my intuitive explanation for the mass energy equivalence. That is why it turns out from valid equations in valid theories of physics that you should find that the radiation slightly increases the mass of an object. It agrees also with phenomenology from the perspective of observers trying to measure mass with a scale in the universe. Albeit, I mean, these are like microscopic vibrations. Obviously, you're not going to notice it with a typical scale. But if you were to, which is why it hasn't been observed before Einstein, but if you were to have that level of precision, I suspect you would find this exact phenomenon happening almost exactly. That would be my current understanding of it anyway. Which feel free to comment below in the description if you have different ideas, or if you want to start the conversation. I'm open to discussing these ideas for the love of physics, if you like physics. So, okay, again, so basically to wrap things up, resonance happens when you have more or less an analogy to constructive interference. Objects have an optimal vibration level or something, which has to do with how much mass is contained in that object. We've talked about an object vibrating as it absorbs radiation. Well, it turns out it doesn't absorb necessarily every vibration equally. Some vibrations are absorbed rather very inefficiently. They do not correspond to efficient coupling. Efficient coupling only happens in very specific integer multiples of particular frequencies that have to do with the atomic or molecular constitution of an object, and essentially that's how massive it is, which is the classical, which is the classical physics understanding of resonance, but it also translates very nicely to quantum mechanics, to a basic understanding of atomic theory. So that's resonance. Resonance is that objects only accept really particular waves. They accept only really specific waves. While they accept the other waves also, but it's not going to resonate very efficiently. It will resonate and absorb most of that energy very efficiently. You will have efficient coupling if it's the resonant frequency specifically, or integer multiples of the resonant frequency. By integer multiple, I mean that resonant frequency, or the double of that resonant frequency or the triple of that integer of that resonant frequency, but not 1.5 times that frequency. It will be that frequency or an integer multiple, 1, 2, 3, 4, 5, but it would never be 4.5 times that resonant frequency. That is essentially the phenomenon of resonance and its relation to mass and mass energy, more or less. So thank you for watching the video. You know, I hope the video was highly informative, and I haven't done a video in a while. You know, if you have feedback or questions, especially physics related questions, you know, feel free to ask them. If you have physics related comments, also feel free to comment down below. As always, like and subscribe to the channel, and see you in the next video.